It started with a gadget for computer memory. In 1969, at Bell Labs, two scientists named Willard Boyle and George Smith were trying to create a new way to store data. They came up with something they called a charge-coupled device, or CCD. It was a silicon chip that could shuffle little packets of electrical charge along its surface. The idea was to represent data, the ones and zeros of a computer, with these charge packets. But they quickly noticed something else. The chip was sensitive to light. When light hit the silicon, it created an electrical charge. The brighter the light, the bigger the charge. They had accidentally invented a light detector. It was a solution in search of a problem. By the 1970s, NASA had a problem. They were building space telescopes and planetary probes. They needed to capture faint light from distant stars and galaxies with incredible precision. Photographic film was not good enough. It was messy, inefficient, and not very sensitive. They needed a digital eye. That's when they turned to the CCD. NASA funded research to improve the technology, making the chips larger, more sensitive, and less prone to electronic noise. These advanced CCDs became the heart of instruments like the Hubble Space Telescope's wide field and planetary camera. A failed memory device became the tool that showed us the deepest, oldest parts of the universe. And it revealed galaxies we never knew existed and helped measure the expansion of the cosmos. This happens a lot in science. An idea from one field, sometimes an accident, gets applied to a completely different problem and changes everything. It opens up a new way of seeing. Brane cosmology is one of those ideas. It came from the abstract world of string theory, a field trying to unite the laws of physics. But when cosmologists started using its concepts, it suggested a new picture of reality, a picture where our entire universe is just a slice in a much larger, higher dimensional space. A picture that is easily one of the wildest in all of physics. Number 22, our universe is a thin membrane. Our universe contains about 2 trillion galaxies. Each of those galaxies, like our Milky Way, holds hundreds of billions of stars. The observable universe stretches over 93 billion light years. And yet, this entire expanse, all this space and matter and energy, might exist on a thin, three-dimensional membrane. This membrane is called a brane, short for membrane. It is the fundamental starting point of Brane cosmology. The idea is that our universe isn't the whole show, it's just a surface. Think of it like the surface of a pond. All the things we know, all the particles and forces we can measure are like lily pads and water striders. They can move around on the surface along the 3 dimensions we experience: length, width, and height. But they can't leave the surface. They are stuck to the brane. This is a radical departure from the standard view of cosmology. The standard view says the universe is everything there is. It's the stage and the play all at once. Brane cosmology says our universe is just one stage, maybe one of many, floating in a larger space. This larger, higher dimensional space is called the bulk. We can't see it or touch it. We are confined to our brain. The particles that make up our bodies, our planet, and our stars are described in string theory as open strings. The ends of these strings are anchored to our brain. This is why we are trapped here. It's not a wall or a cage we can break through. It's a fundamental property of our existence. The very stuff we are made of is physically attached to this 3-dimensional slice of reality. This concept was first seriously explored in the mid-1990s by physicists like Joseph Polchinski, who showed that these branes were a necessary part of M-theory, a deeper version of string theory. Before that, branes were just obscure mathematical objects. Polchinski's work in 1995 showed they were real dynamic things that could hold energy and anchor strings. This discovery turned them from a curiosity into a central component of the theory. So why would anyone propose such a strange idea? It wasn't just for shock value. It was proposed to solve some very deep problems in physics. One of the biggest is the weakness of gravity. Another is the nature of the Big Bang. By confining our universe to a brane, physicists found new and elegant ways to think about these old puzzles. It suggests that what we call the universe is really just our local neighborhood. The true reality, the bulk, could be much larger, older, and stranger than we can ever directly experience. All of history, every star that has ever shone, every life that has ever been lived, has played out on this thin film. Number 21, there are extra dimensions of space all around us. The world we see has 3 spatial dimensions. You can move forward and backward, left and right, up and down. That's it. For centuries, this was an unquestioned fact of reality, but Brane Cosmology is built on the idea that this is wrong. It claims there are more dimensions of space. They are hidden from us, but they are just as real as the 3 we know. This isn't just a science fiction trope, it's a core requirement of the theory. The idea of extra dimensions is actually quite old. It goes back to the 1920s. A Polish physicist named Theodore Kaluza sent a letter to Albert Einstein. Kaluza had an amazing idea. He suggested that if the universe had a 4th dimension of space, just one extra one, he could unite Einstein's theory of gravity with James Clerk Maxwell's theory of electromagnetism. It was the first attempt at a unified field theory. Einstein was intrigued but skeptical. A few years later, a Swedish physicist named Oskar Klein refined the idea. He proposed that this extra dimension was hidden from us because it was curled up into a tiny circle. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you get very close, you see it has a second dimension, the circular part you can go around. Klein suggested the extra dimension was like that, but curled up to a size smaller than an atom, about 10 raised to the power of 33 centimeters. That's why we don't see it or experience it. Our clumsy, large-scale bodies can't perceive such a tiny scale. String theory took this idea and ran with it. To be mathematically consistent, string theory requires not just one extra dimension, but 6 or 7 of them. So in total, there would be 10 or 11 dimensions of spacetime. For decades, physicists assumed that these extra dimensions, like in the Kaluza-Klein idea, must be curled up and incredibly small. This was the standard picture. Brane Cosmology challenged this. It said the extra dimensions don't have to be small. They could be large. They could even be infinite. The reason we don't experience them is because we are stuck on our brane. The particles and forces that make up our world are confined to 3 dimensions. We are like characters in a book. We can move around on the 2D page, but we can't perceive the 3rd dimension of the room the book is in. Similarly, we are stuck on our 3D brane, unable to move into the extra dimensions of the bulk even if they are right next to us. Only one force is thought to be able to travel into these extra dimensions, gravity. This is a crucial point that Brane Cosmology uses to explain some of the universe's biggest mysteries. The existence of these extra dimensions is not just a weird side effect of the theory. It's the entire foundation upon which it is built. It changes the definition of space. Space is not just the 3D void between stars. It's a vast higher dimensional arena, and our entire universe is just a tiny subspace within it. Number 20, gravity isn't weak, it's just spread thin. Gravity is ridiculously weak. A small refrigerator magnet can lift a paperclip, defeating the gravitational pull of the entire Earth. Compared to the other fundamental forces, gravity is an outlier. The electromagnetic force is about 10 raised to the power of 36 times stronger. The strong nuclear force, which holds atomic nuclei together, is even stronger. This vast difference in strength is called the hierarchy problem, and it's one of the deepest mysteries in physics. Why is gravity so feeble? Brane Cosmology offers a startling answer. Gravity isn't weak at all. It's just as strong as the other forces. We only experience a tiny fraction of its true power because most of it leaks away into the extra dimensions. Here's how it works. The standard model of particle physics describes the forces of nature as being carried by particles. Electromagnetism is carried by photons. The strong and weak nuclear forces are carried by gluons and W and Z bosons. In string theory, these particles correspond to open strings, with their ends attached to our brane. This is why their forces are so strong. Their entire influence is concentrated right here in our 3 dimensions. Gravity is different. The particle that carries the gravitational force is called the graviton. In string theory, the graviton corresponds to a closed loop of string. A closed loop has no ends to anchor to the brane. This means the graviton is not stuck. It is free to travel anywhere, not just in our 3 dimensions, but throughout the entire higher dimensional bulk. Imagine our universe is a large, thin sheet of metal. If you strike the sheet, the sound waves representing the other forces travel along the surface. All their energy is confined to the 2D sheet. Now, imagine you hold a hot object near the sheet. The sheet will warm up representing gravity, but most of the heat radiates away into the 3D room around it. The effect on the sheet itself is weak. This is the Brane world explanation for the hierarchy problem. The other forces are trapped on the brane, so we feel their full strength. Gravity is free to roam the bulk, so its strength gets diluted across all the extra dimensions. We only feel the small part that happens to act on our brane. This idea was developed into a specific model in 1998 by 3 physicists, Nima Arkani Hamid, Savas Dimopoulos, and Gia Diwali. Their model, known as the ADD model, proposed that the extra dimensions could be quite large, perhaps as big as a millimeter. This was a shocking idea. If there was a millimeter-sized extra dimension all around us, why wouldn't we have noticed? The answer is that only gravity can access it. We can't see it or touch it. But if this idea is right, it means that at very small distances, gravity should get much stronger. And physicists have been conducting experiments to test the law of gravity at sub-millimeter scales, looking for any deviation from what Newton predicted. So far, they haven't found one, but the search continues. The idea that gravity's weakness is just an illusion caused by hidden dimensions remains one of the most compelling parts of Brane cosmology. Number 19, parallel universes are less than a millimeter away. The concept of parallel universes is usually confined to science fiction. Brane cosmology makes it a concrete physical possibility. It suggests that our universe, our brane, may not be the only one. There could be other branes, other universes floating in the bulk right alongside ours. They could be separated from us by a tiny distance less than the width of a human hair through the extra dimensions. We would be completely unaware of their existence. In this picture, the bulk is a vast space that can contain many branes. Each brane is its own self-contained universe, with its own set of particles and its own version of physics. The inhabitants of one brane would be completely unable to see or interact with the inhabitants of another. Why? Because the particles and forces that make up our world, like light, are stuck to our brane. The light from a parallel universe can't travel across the bulk to reach our eyes. We are essentially living in a house with paper-thin walls, but we can't see, hear, or touch our neighbors because the signals we use to perceive the world can't pass through the walls. There is one exception: gravity. Because gravitons are not stuck to any single brane, they can travel through the bulk. This means that a massive object in a parallel universe, like a star or a galaxy, would exert a gravitational pull on our universe. We wouldn't be able to see the star, but we could feel its gravity. This has led to some interesting speculation. Could the mysterious substance known as dark matter be evidence of a parallel universe? Dark matter is a form of matter that we can't see, but we know it's there because of its gravitational effects on galaxies. Perhaps dark matter isn't in our universe at all. Perhaps it's just normal matter, like stars and planets residing on a nearby brane. We see its gravity leaking across the gap between branes, but we can't see the matter itself because its light is trapped on its own brane. This idea was part of the original ADD model from 1998. The model allows for the possibility of these parallel branes. The distance between them would depend on the specific geometry of the extra dimensions. In some versions, the distance could be microscopic. The implications are profound. It would mean that reality is layered. We live our lives completely oblivious to entire other worlds existing a fraction of a millimeter away. There would be no way to communicate with them or travel to them. Our only connection would be through the subtle, persistent pull of gravity, a faint whisper from a neighboring cosmos. And it redefines what it means to be alone in the universe. We might be surrounded by an infinite number of other worlds, but we are forever isolated on our own thin slice of existence. Number 18, the Big Bang was two universes colliding. The standard Big Bang theory says the universe began from an infinitely hot, infinitely dense point called a singularity. It doesn't say what came before the singularity or what caused it. The theory is silent on the ultimate origin. Brane Cosmology offers a dramatic alternative. The Big Bang was not the beginning of time. It was a violent, cataclysmic event in a much older, larger reality. It was the collision of two parallel universes. This idea is part of a model called the ekpyrotic universe, first proposed in 2001 by Paul Steinhardt, Justin Khoury, Bert Overoot, and Neil Turok. The name ekpyrotic comes from an ancient Greek philosophical concept of a cosmic fire that cyclically destroys and recreates the world. In this model, our universe is one of two branes that exist in the bulk, separated by a tiny gap. For eons, these two branes float parallel to each other, but they are not static. There is a force between them, a kind of spring-like potential energy that slowly pulls them together. Over an incredibly long period of time, they drift closer and closer. Eventually, they collide. This collision is not like two solid objects crashing. It's a collision of the very fabric of space-time. The immense kinetic energy of the collision is converted into the matter and radiation that fills a new universe. From the perspective of an observer on one of the branes, this event looks exactly like a Big Bang. It is a moment of extreme heat and density, followed by rapid expansion and cooling. The collision smooths out the branes, explaining why our universe is so uniform on large scales, a problem that standard cosmology solves with a concept called inflation. After the collision, the branes bounce apart. The force between them pushes them away again, and they begin another long, slow cycle of drifting apart and then coming back together. This leads to a cyclic model of the universe. The Big Bang was not a one-time event. It is part of an endless series of collisions and bounces. Our universe has been created and destroyed over and over again for eternity. This completely changes our perspective on cosmic history. It provides an answer to the question of, what came before the Big Bang? The answer is the previous cycle of the universe. There was no beginning of time. Time stretches infinitely into the past and infinitely into the future. Our entire cosmic history is just one chapter in an endless book. The model is controversial and still debated among cosmologists, but it provides a compelling physical mechanism for the origin of our universe, replacing the mysterious singularity of the standard model with the tangible, if epic, clash of two worlds. Number 17, we could make tiny black holes at the LHC. Black holes are usually thought of as giant monsters formed from the collapse of massive stars. They are so dense that nothing, not even light, can escape their gravitational pull. Creating a black hole on Earth seems impossible. You would need to compress Mount Everest down to the size of an atom. But if Brane Cosmology is correct, it might be possible to create microscopic black holes right here on Earth in a particle accelerator like the Large Hadron Collider LHC at CERN. The reason for this goes back to the weakness of gravity. You know, in our normal 3D world, gravity is incredibly weak. This is why it takes a star dozens of times more massive than our sun to collapse into a black hole. The gravitational force just isn't strong enough to overcome the other forces in smaller objects. But in brane world scenarios, especially the ADD model with large extra dimensions, gravity isn't actually weak. Its true strength is just diluted across the bulk. At very small distances, on the order of the size of the extra dimensions, gravity's full strength is unleashed. It becomes much, much stronger, comparable to the other forces. The LHC smashes protons together at nearly the speed of light. These collisions concentrate a huge amount of energy into a tiny space. If two particles pass close enough to each other in one of these collisions, the gravitational attraction between them could become incredibly strong, thanks to the influence of the extra dimensions. This powerful gravity could be enough to cause the energy of the collision to collapse in on itself and form a tiny microscopic black hole. The energy required to do this would be far less than what standard physics predicts, potentially within the range of the LHC. The idea of creating black holes in a lab understandably caused some public concern when it was first discussed in the early 2000s. People worried that one of these mini black holes could escape and devour the Earth. However, physicists are confident this is not a risk. These black holes would be incredibly small, much smaller than a proton. They would also be incredibly unstable. According to Stephen Hawking's theory of black hole radiation, smaller black holes evaporate much faster than large ones. A microscopic black hole created at the LHC would evaporate almost instantly, in about 10 raised to the power of 27 seconds. It would decay into a spray of ordinary particles that would be detected by the LHC's sensors. Finding these mini black holes would be a revolutionary discovery. It would be direct evidence for the existence of extra dimensions. The specific way they decay would give us information about the number and size of these dimensions. So far, the LHC has not seen any evidence of mini black hole production. This has allowed physicists to rule out certain versions of Brane cosmology with very large extra dimensions. But the search continues. The possibility, however remote, that we could create a fleeting black hole in a lab remains one of the most exciting and tangible predictions of this wild theory. Number 16, dark energy is the force pushing universes apart. In 1998, astronomers made a shocking discovery. The expansion of the universe is not slowing down, as everyone had expected. It's speeding up. Some mysterious anti-gravitational force is pushing everything apart at an ever-increasing rate. They named this force dark energy. It is the dominant component of the universe, making up about 70% of its total energy content, but we have no idea what it is. It is perhaps the single biggest mystery in all of science. Brane cosmology provides a possible explanation, and it's as strange as the problem itself. Dark energy could be the energy of the empty space between our brain and another. In the cyclic model of the universe, where two brains collide and bounce, there is a force that governs their motion. This force is stored as potential energy in the gap between the branes in the bulk. When the branes are far apart, this energy is low. As they are pulled together, the energy changes. After they collide and bounce, this interbrain force is what pushes them apart again. This repulsive force acting between the brains would manifest itself on our brain as an acceleration of our own cosmic expansion. Think of two trampoline sheets held parallel to each other. The tension in the springs connecting them represents the interbrain force. After you push them together and they bounce apart, that spring tension is what drives them away from each other. For someone living on the surface of one trampoline, this would feel like their world was being stretched out or expanding at an accelerating rate. In this view, dark energy is not some mysterious substance filling our universe. It is an external force, a consequence of our universe's interaction with another unseen universe through the bulk. This idea connects the origin of the universe, the Big Bang collision, with its ultimate fate, endless acceleration. The same force that caused the Big Bang is now driving the cosmic acceleration we observe today. Paul Steinhardt, one of the architects of the cyclic model, has argued that this provides a more natural explanation for dark energy than the standard cosmological model. In the standard model, the value of dark energy is a huge puzzle. Theoretical calculations predict it should be about 10 raised to the power of 120 times stronger than what we observe. This is known as the cosmological constant problem, and it's the worst prediction in the history of physics. The Brane world model, by tying dark energy to the dynamics of extra dimensions, offers a new way to approach this problem, potentially explaining why its value is so small. It recasts the biggest puzzle in cosmology as a question about the geometry of hidden dimensions and the forces between parallel worlds. Number 15. The extra dimensions might be warped, not flat. When we first think of extra dimensions, we usually imagine them as being just like our own, flat and straightforward. But what if they aren't? What if the geometry of the bulk is curved or warped? In 1999, two physicists, Lisa Randall and Raman Sundram, proposed a new kind of brane world model that did just this. Their model, known as the Randall-Sundram or RS model, suggested a universe with just one extra dimension, but this dimension was severely warped. This warping had a dramatic effect on physics, and it provided a completely new solution to the hierarchy problem. The RS model describes a setup with two branes at either end of a small, finite fifth dimension. One brane is called the Planck brane or gravity brane, and the other is the TeV brane or our brane. The key idea is that the geometry of the space between them is not flat Euclidean space. It is a slice of what is known as anti-de Sitter space, which has a negative curvature. This curvature creates a warp factor. As you move away from the Planck brane and towards our brane, the scale of energy and distance gets exponentially stretched. Think of a distorted mirror at a funhouse. As you walk towards it, your reflection might get stretched out taller and thinner. The warped fifth dimension acts in a similar way on the fundamental forces. Gravity originates on the Planck brane. As it travels through the warped dimension to reach us on our brane, its strength is diluted exponentially by this warp factor. By the time it gets to us, it appears incredibly weak. The other forces, meanwhile, are stuck on our brane, so they are not affected by the warping and retain their full strength. This is a very efficient way to solve the hierarchy problem. The ADD model required large extra dimensions to dilute gravity. The RS model can do it with a tiny microscopic extra dimension, as long as it's sufficiently warped. The distance between the two branes could be just 10 raised to the power of 30 centimeters, far smaller than a proton. This makes the model much harder to test experimentally with tabletop gravity experiments. Unlike the ADD model, it doesn't predict that gravity's law will change at the millimeter scale. The RS model has other fascinating consequences. It predicts the existence of new, heavy particles that are copies of our known particles called Kaluza-Klein gravitons. These would be gravitons that have momentum in the extra dimension. They would be massive from our 3D perspective and could potentially be created at the LHC. Finding these particles would be a smoking gun for this type of warped extra dimension. The Randall-Sundram model showed that there was more than one way to build a brane universe. The extra dimensions didn't have to be large and flat. They could be small and twisted into strange geometries, creating effects that could explain some of the deepest puzzles in physics. Number 14, string theory needs branes to make sense. Our Brane Cosmology didn't just appear out of nowhere. It grew out of string theory, the leading candidate for a theory of everything. For a long time, string theory was just about strings. It proposed that the fundamental constituents of reality were not point-like particles, but tiny, one-dimensional vibrating strings. Different vibrations of the string would appear to us as different particles, like electrons, photons, or quarks. The theory was elegant, but it had its own problems. One of them was that it actually predicted 5 different consistent versions of string theory. This was an embarrassment. A theory of everything should be unique. The breakthrough came in the mid-1990s, during what is called the second superstring revolution. A physicist at the Institute for Advanced Study named Edward Witten proposed that these 5 different string theories were not competing theories. They were actually just different aspects of a single, deeper, underlying theory. He called this mysterious new theory M theory. Nobody knows the full equations of M theory, but we know some of its properties. One of its most important properties is that it lives in 11 dimensions of spacetime. And another is that it doesn't just contain strings, it contains higher dimensional objects called p-branes, where stands for the number of spatial dimensions the brane has. A 0 brane is a point. A 1 brane is a string. A 2 brane is a membrane. and so on, all the way up to a 9 brane. This was a huge shift. The theory was no longer just about strings. These branes were just as fundamental. Joseph Polchinski's work around the same time showed that branes were not just mathematical curiosities, they were dynamic objects where the ends of open strings could attach. This was the crucial link. Suddenly, branes were a necessary part of the theory. Without them, string theory was incomplete and inconsistent. They were needed to explain certain symmetries and dualities that Witten had uncovered, which showed how the 5-string theories were related to each other. This is what gave physicists the confidence to build cosmological models based on branes. The idea that our universe could be a 3-brane was no longer just a wild guess. It was a possibility that was directly suggested by the most fundamental theory of physics we have. The M theory provided the theoretical playground. It said that a reality with branes of various dimensions floating in an 11-dimensional space was not only possible but required. The cosmologists then took that playground and asked a simple question: what if we are living on one of those branes? This question led to all the wild ideas of Brane cosmology, from colliding universes to leaking gravity. It all started because a theory of tiny strings needed bigger membrane-like objects to hold it all together. Number 13, cosmic strings could be branes from another dimension. Cosmic strings are not the same as the fundamental strings of string theory. They are hypothetical defects in the fabric of space-time, a bit like the cracks that form when water freezes into ice. Cosmologists have speculated for decades that these objects might have been formed during phase transitions in the very early universe. They would be incredibly thin, but also incredibly dense, stretching across vast regions of space. If they exist, they would bend light in a very specific way, so astronomers have been searching for their gravitational lensing effects for years without success. Brane Cosmology offers a new and bizarre way to think about what these cosmic strings might be. They might not be defects in our universe at all. They could be branes from a higher dimension poking through our own. In M theory, the bulk contains branes of many different dimensions. Our universe is a 3-brane, but the theory also allows for 1-brane strings and 2-branes membranes and so on. Now, imagine a higher dimensional brane, say a 4-brane, that exists in the bulk. What happens if this 4-brane intersects with our 3-brane universe? The intersection of a 3D space and a 4D space would be a 2D surface, a membrane. If a 5-brane intersected our universe, the intersection would be a 3D volume. This idea, called intersecting branes, provides a mechanism to generate the particles and forces of the standard model. But what if a 1-brane from the bulk, a fundamental string from M theory, passed through our universe? Its intersection with our 3-brane would be a point, a 0-brane. What if a 2-brane from the bulk intersected our universe? The intersection would be a line, a 1-brane. This line, a slice of a higher dimensional object, would appear to us as a cosmic string. It would be a place where the physics of the bulk leaks into our world. This idea was explored by physicists like Alexander Vilenkin. It suggests that if we ever did detect a cosmic string, it could be a piece of evidence for a much larger reality. It would be like finding a mysterious, impossibly thin thread running through our world. By studying it, we might be able to learn something about the object it is a slice of, and therefore something about the nature of the bulk and the extra dimensions. This also leads to an even stranger possibility. In some models, our entire universe could be the intersection of 2 higher dimensional branes. For example, the collision of 2 4-branes in a 5D bulk could create a 3-brane SR universe at their intersection, along with all the matter and energy within it. This recasts our entire existence not as a fundamental object, but as a feature created by the interaction of even larger unseen realities. Number 12, the laws of physics might be different, off the brain. We take the laws of physics for granted. The speed of light is constant. The charge of an electron is the same everywhere. These are the fundamental constants that make our universe work. But if our universe is just a three-brane in a larger bulk, this raises a strange question. Are these laws universal, or are they just local bylaws specific to our brain? It's possible that the laws of physics as we know them are a feature of our brain, and that in the bulk, or on other brains, the laws could be completely different. The values of the fundamental constants, like the strength of the electromagnetic force or the masses of particles, are determined in string theory by the shape and size of the curled up extra dimensions. This is known as the moduli of the theory. The geometry of these extra dimensions is not fixed, it can change. Each different possible geometry would lead to a different set of physical laws. In the context of Brane cosmology, the specific properties of our three-brane, its tension, its position in the bulk, how it is wrapped around the extra dimensions, would determine the physics that we observe. This means that a parallel brane just a millimeter away could have a completely different version of physics. On that brane, the strong force might be weaker, meaning atoms could not form, or gravity could be stronger, meaning stars would burn out in an instant. Most of these other universes would likely be sterile and unable to support complex structures, let alone life. Our universe just happens to be on a brane with the right properties. This is a version of the anthropic principle. We find ourselves in a universe with these specific laws because if the laws were different, we wouldn't be here to observe them. This idea is part of the string theory landscape. The theory seems to allow for a vast number of possible solutions, perhaps 10 raised to the power of 500 or more. Each solution corresponds to a different vacuum state, with different curled up dimensions and different physical laws. Each of these solutions could be realized on a different brane in the multiverse. Our Big Bang, the collision of two branes, might have just been one event that created one such pocket universe with one particular set of laws. Other collisions elsewhere in the bulk could have created other universes with other laws. This is a profound and somewhat unsettling idea. It suggests that the laws of nature are not absolute and eternal. They are environmental, they are a product of our specific location in a much larger, more varied cosmos. It takes the Copernican principle, the idea that we are not in a special place in the universe, to its ultimate conclusion. Not only are we on a typical planet orbiting a typical star in a typical galaxy, but we may also be living in a universe with a typical, randomly selected set of physical laws from a near infinite menu of possibilities. Number 11, information could be lost to other universes. One of the most sacred principles in physics is the conservation of information. It means that information can never be truly lost. If you burn a book, all the information contained in its pages is not destroyed. It is just scrambled and encoded in the smoke, ash, and heat that is released. In principle, if you could track every single one of those particles, you could reconstruct the original book. Stephen Hawking famously challenged this idea with his theory of black hole evaporation. He claimed that when a black hole evaporates, the information about what fell into it is lost forever. This started a decades-long debate known as the black hole information paradox. Most physicists now believe that the information is somehow preserved. Brane cosmology introduces a new and troubling way for information to be lost. If tiny black holes can be created in particle collisions at the LHC, as some models predict, they could provide a channel for information to leave our universe entirely. When one of these mini black holes forms on our brane, it would begin to evaporate by emitting Hawking radiation. Some of this radiation would be emitted as particles that are stuck to our brane, like photons and electrons. We could detect these, but because the black hole exists in the full higher dimensional space, it could also emit gravitons. And these gravitons are not stuck to our brane, they could fly off into the bulk. This means that some of the mass, energy, and information of the particles that created the black hole would be radiated away into the extra dimensions, lost from our universe forever. From our perspective, it would look like a violation of the conservation of energy and information. Or we would see a certain amount of energy go into the collision and a smaller amount come out. The rest would have vanished into the bulk. This is a testable prediction. If physicists at the LHC ever see events where there appears to be missing energy, this could be a sign of something being sent off into extra dimensions. Such signatures are actively being searched for. Of course, there are other, more mundane explanations for missing energy in a particle collision, like the production of neutrinos, which are very hard to detect. But if a consistent pattern of energy loss were seen in the types of events where mini black holes are expected to form, it would be powerful evidence for the brane world scenario. Or it would mean that our universe is not a closed system, it is leaky, things can escape, carrying information with them into a higher dimensional reality that we can never access. The fundamental rule that information is never lost might only apply to the multiverse as a whole, not to our individual corner of it. Number 10, we are made of the lowest form of string. In string theory, not all strings are created equal. The theory is built on a concept called supersymmetry. This is a symmetry that relates the two fundamental types of particles in nature, fermions and bosons. Fermions are the particles of matter, like electrons and quarks. Bosons are the particles that carry forces, like photons and gluons. Supersymmetry predicts that every known particle has a superpartner with different properties. The electron, a fermion, would have a superpartner called the selectron, a boson. The photon, a boson, would have a superpartner called the photino, a fermion. Brane Cosmology, which is born from string theory, incorporates this idea, but it adds a twist. It suggests that our entire world, all the matter and non-gravitational forces we see, is made of one kind of string, while gravity is made of another. The particles of the standard model, the quarks, electrons, photons, gluons, player, are all excitations of open strings. These are the strings that have endpoints, and those endpoints, crucially, are stuck to our three-brane. This is what confines us to our universe. These open strings are, in a sense, the workhorses of our world. The gravity, on the other hand, is different. The graviton is an excitation of a closed string, a loop with no endpoints. Because it has no ends, it is not tied down to our brane, it is free to roam the entire bulk. This distinction between open and closed strings is fundamental to how Brane Cosmology works. It is the reason why gravity is special and can feel the extra dimensions while the other forces cannot. This leads to a strange sort of hierarchy. Our existence is tied to the lesser form of string, the open string that is bound and confined. The higher form of string, the closed loop, is free and untethered, able to experience the full, higher dimensional reality. We are, in a sense, the Flatlanders, unable to perceive the true scope of the world, while gravity is the 3D being that can see everything. This idea also has consequences for what we might find at particle accelerators. If supersymmetry is real, we should be able to produce the superpartner particles. In many brane world models, these superpartners might behave differently from their standard model counterparts. Some of them might be able to travel short distances into the bulk before decaying back onto our brane. Their existence and properties are deeply tied to the geometry of the extra dimensions and the nature of the brane itself. So the search for supersymmetry at the LHC is also indirectly a search for evidence of the stringy underpinnings of Brane Cosmology. It's a search for a deeper level of reality, one where the distinction between matter and forces is blurred, and where our entire world is built from strings that are fundamentally anchored to a thin membrane in a higher space. Number 9, the bulk could be infinite. When physicists first started thinking about extra dimensions, they usually assumed they had to be small and finite, curled up in a tiny circle. The ADD model challenged this by suggesting they could be large, up to a millimeter in size, but still finite. The Randall-Sundrum model went back to a small, finite dimension, but made it warped. But there is a third, even wilder possibility. The extra dimensions could be infinite in extent. Our three-brain universe could be a finite island floating in an infinitely large, higher dimensional sea. This idea was developed in a model proposed in 2000 by Gregory Gabadadze and Giadvali, building on earlier work by Diwali, Gabadadze, and Massimo Parati. It is known as the DGP model. The setup is simple. Our three-brain exists within a four-dimensional plus time bulk that is flat and infinite. The strange thing is what this does to gravity. On our brain, gravity behaves in a four-dimensional way 3 space plus 1 time. Out in the bulk, it behaves in a 5-dimensional way 4 space plus 1 time. The model is constructed in such a way that at short distances, gravity is stuck to the brain. The graviton is temporarily trapped, and gravity behaves like we expect, following the inverse square law. But at very large cosmological distances, gravity starts to leak into the infinite bulk more effectively. This leakage causes gravity to become weaker than predicted by Einstein's theory of general relativity over vast scales. And this weakening of gravity at large distances has a remarkable consequence. It causes the expansion of the universe to accelerate. The DGP model, therefore, provides an explanation for dark energy without invoking any mysterious new substance or energy field. The observed cosmic acceleration is not being caused by something pushing the universe apart. It is being caused by gravity itself becoming weaker on cosmic scales, allowing the universe's initial expansion to take over. This is a completely different approach to the problem of dark energy. Instead of modifying the contents of the universe, it modifies the law of gravity itself. It is a theory of modified gravity. The model is very specific in its predictions. It predicts that the expansion history of the universe should be different from that predicted by the standard dark energy model. Astronomers are trying to test this by making precise measurements of distant supernovae and the large-scale structure of galaxies. So far, the evidence slightly favors the standard model with a cosmological constant, but the DGP model has not been completely ruled out. It remains a fascinating possibility. If it were true, it would mean that our universe is fundamentally unstable. Over immense timescales, all the gravitons binding our brain together would eventually leak away into the infinite bulk, and our universe would dissolve. It would also mean that the space we think of as our universe is just an infinitesimal slice of a much larger infinite reality that surrounds us. Number 8. The brain itself has properties like tension. In Brane Cosmology, our universe is not just a passive stage. The brain itself is a physical object. And like any physical object, it has properties. One of its most important properties is brain tension. This is a measure of the brain's stiffness or resistance to being curved or stretched. It's similar to the surface tension of a water droplet, which is what holds the drop together in a spherical shape. The brain tension is a fundamental parameter of the theory, and its value has a huge impact on both cosmology and particle physics. The tension of our brain contributes to the overall energy density of the universe. In the context of general relativity, energy and pressure are sources of gravity. The brain's tension acts as a form of energy, and so it curves the space-time on the brain. In fact, in the Randall-Sundrum model, it is a delicate balance between the brain tension and the curvature of the bulk spacetime that keeps the whole system stable and results in the flat universe we observe. If the tension were even slightly different, the model would not work. The brain tension also affects how gravity behaves. In models with large extra dimensions like the ADD model, the value of the brain tension helps determine the scale at which gravity deviates from Newton's laws and becomes higher dimensional. A higher tension brain would hold onto gravity more tightly, meaning you would have to probe smaller distances to see the effects of the extra dimensions. Furthermore, the brain tension sets the energy scale for the physics of the brain itself. The vibrations of the brain, like the ripples on a pond's surface, would appear to us as new types of particles. The energy, and therefore the mass, of these particles would be determined by the brain tension. If the tension is very high, these particles would be too heavy to create in our current experiments. This idea that our universe has a physical property like tension is a strange one. We are used to thinking of space as a vacuum, as emptiness. Brane cosmology says the vacuum of our universe is not empty, it is the fabric of the brain itself, and this fabric has a certain rigidity. This also has implications for the very early universe. The brain's tension would have played a major role in the dynamics of the Big Bang, whether it was caused by a collision or some other process. Some theories even propose that the inflationary expansion of the early universe was driven by the changing tension of a brain. The idea transforms the universe from a mere container for matter and energy into a dynamic object with its own intrinsic physical characteristics. Number 7, we might live on a domain wall. The term brain is very general, but what is it actually made of? Where does it come from? In physics, there is a concept known as a domain wall. This is a type of topological defect that can form when a system undergoes a phase transition. A familiar example is a magnet. Above a certain temperature, the Curie temperature, the magnetic moments of the atoms are all pointing in random directions. As the magnet cools, these moments all line up in the same direction, but it's possible for different regions of the magnet to line up in opposite directions. The boundary between a region of north up and a region of south up is a domain wall. It's a thin 2D surface where the magnetic field is rapidly changing. Some physicists have proposed that our 3-brane universe could be exactly this, a domain wall in a higher dimensional space. The idea is that the bulk is filled with some kind of field called a scalar field. This field could have undergone a phase transition in the very early history of the multiverse. As the bulk cooled, this field would have settled into a stable vacuum state. But, just like in the magnet, different regions of the bulk could have settled into different vacuum states. Our universe would be the 3D boundary, the domain wall, between two different regions of the bulk. This provides a natural mechanism for trapping matter. Many theories of particle physics contain particles that would naturally get stuck on such domain walls. The properties of the wall, determined by the nature of the scalar field in the bulk, would dictate the properties of the particles that live there. In a sense, the particles of the standard model would be the excitations of this domain wall. They would be the ripples and kinks in the boundary between two different kinds of higher dimensional vacuum. This picture was explored in the original Randall-Sundrum model. The two branes in their setup, the Planck brane and our brane, can be thought of as domain walls. This provides a more concrete physical basis for what a brane is. It's not just a abstract mathematical surface. It is a physical interface created by the dynamics of fields in the bulk. This also leads to some testable consequences. For example, the collision of two such domain walls would release a tremendous amount of energy, providing a natural mechanism for the hot Big Bang in the ekpyrotic and cyclic models. It also suggests that the vacuum of our universe is not truly stable. It is only stable because it is a boundary. It's possible that under certain conditions this wall could be destroyed, or it could interact with other defects in the bulk, leading to cosmological events far stranger than anything we have yet imagined. Number 6, the problem it tries to solve is staggeringly large. The hierarchy problem, the question of why gravity is so weak, is not just a small discrepancy. The numbers involved are astronomical. The natural energy scale for a theory of quantum gravity, known as the Planck scale, is about 10 raised to the power of 19 giga-electron-volts GeV. The energy scale at which the weak nuclear force and electromagnetism unify, the electroweak scale, is only about 100 GeV. There is a gap of 17 orders of magnitude. That's a 100 quadrillion times difference. In physics, such a huge, unexplained gap between two fundamental scales is seen as a major problem. It feels unnatural. It's like building a skyscraper where the foundation is made of granite, but the rest of the building is made of styrofoam. It seems like something must be missing. Physicists have spent decades trying to explain this gap. One of the most popular ideas was supersymmetry. In supersymmetric theories, the quantum effects of standard model particles are precisely cancelled out by the effects of their superpartners. This cancellation can stabilize the electroweak scale and protect it from being pulled up to the enormous Planck scale. It solves the hierarchy problem neatly. The problem is, despite years of searching at the LHC, not a single superpartner particle has been found. This has led many physicists to become disillusioned with this solution. Brane Cosmology offers a completely different way out. It doesn't try to protect the electroweak scale from the Planck scale. Instead, it brings the Planck scale down. In models with large extra dimensions, like the ADD model, the true fundamental scale of gravity is not the high Planck scale we observe. The true scale is much lower, perhaps as low as the electroweak scale itself, around 1 TeV 1000 GeV. There is no hierarchy in the fundamental theory. The huge Planck scale that we measure in our 3D world is just an illusion. It's an effective scale that appears large because we are not accounting for the fact that gravity is spreading its influence over the extra dimensions. This is a radical shift in perspective. It says that the problem is not with our theory of particles, but with our theory of space-time. We have been miscalculating the strength of gravity because we have been assuming the world is three-dimensional. Once you account for the extra dimensions, the fundamental scale of gravity is brought down to a much more reasonable level, and the hierarchy problem simply vanishes. This is the primary motivation for these kinds of brain world models. They were not invented just to be strange. They were invented to solve what is arguably the biggest and most glaring fine-tuning problem in modern particle physics. The sheer size of the number involved, that factor of 10 raised to the power of 17 is what drives physicists to consider such wild and unconventional ideas about the nature of reality. Number 5, it redefines the very meaning of fundamental. For centuries, the goal of physics has been reductionism. To understand a complex system, you break it down into its smallest, most fundamental parts. We broke matter down into molecules, then atoms, then electrons and nuclei, then protons and neutrons, and finally quarks. We believe these particles, along with a few others, are the fundamental, indivisible building blocks of reality. Brane Cosmology challenges this entire picture. It suggests that the particles and forces we call fundamental might not be fundamental at all. They could be collective behaviors or excitations of a higher dimensional object, our brain. Think about the concept of a wave on the ocean. A water wave has properties like wavelength and amplitude. It can carry energy, it can interact with other waves. To a creature that lives on the 2D surface of the ocean and can't perceive the water itself, these waves might seem like fundamental entities. But we know that a wave is not a fundamental thing. It is a collective motion of a huge number of more fundamental things, water molecules. The wave is an emergent phenomenon. Brane Cosmology allows for the possibility that our entire universe is an emergent phenomenon. The particles we study in our accelerators, the quarks, electrons, and photons, might not be the ultimate reality. They could be the ripples on our brain vibrations of the brain's fabric itself. The laws of physics that govern their interactions would not be fundamental laws of the multiverse, but rather the rules of the game for how these ripples behave on this particular surface. This is especially true in models where our brain is a domain wall. The properties of our particles would be determined by the properties of the higher dimensional field that creates the wall. Different domain walls could support different kinds of particles and forces. This would mean that asking, what is an electron made of, might be the wrong question. The right question might be, what kind of disturbance in the fabric of our three brain do we label as an electron? This perspective shifts the focus of fundamental physics. The ultimate reality would not be the particles of the standard model, but the bulk spacetime and the branes within it. The truly fundamental laws would be the laws of M-theory that govern the dynamics of the bulk. The standard model would be demoted from a theory of fundamental particles to an effective theory that describes the low-energy physics on one specific three-brane in a vast multiverse. This is a humbling idea. It suggests that even if we complete the standard model and understand all its particles and forces perfectly, we may only be scratching the surface. We may only be understanding the behavior of the shadows on the wall of Plato's cave, while the true reality of the bulk remains forever beyond our direct grasp. Number 4, time itself might have started at the collision. The idea of a cyclic universe with endless bounces and collisions seems to solve the problem of the beginning of time. It says there was no beginning, but there are subtle problems with this. One of the fundamental laws of thermodynamics, the second law, states that entropy, a measure of disorder, always increases in a closed system. If the universe has been cycling forever, it should have produced an infinite amount of entropy. The universe would have reached a state of maximum disorder, a heat death, an infinitely long time ago. So how can the universe be in the relatively ordered state we see today? The creators of the cyclic model have proposed a clever way around this. They argue that the universe is not a closed system in the traditional sense. The key is the expansion phase between bounces. During this long, slow phase driven by dark energy, the universe expands to become enormous, cold, and almost perfectly empty. The expansion smooths everything out and dilutes the entropy. By the time the next collision happens, the brane is essentially reset to a very low entropy state. The entropy is not destroyed, but it is spread out over such a vast volume that the effective entropy density on the brane at the start of the next cycle is tiny. But there is another, more radical way to think about it. What if time, as we measure it, is a property of our brane? In this view, time might not exist in the bulk in the same way. The bulk might have a static, timeless geometry. The passage of time that we experience could be a phenomenon that is triggered by the collision of branes. In this scenario, the collision is not just the event that creates the matter and energy of our universe. It is the event that sets the clock of our universe ticking. Before the collision, there was no before in a temporal sense on our brane. The concept of time simply didn't apply. The collision is the true genesis event, the moment that dimensionality, locality, and causality, as we know them, emerge on the brane. Time begins at t=0 with the Big Bang, and the arrow of time is established by the subsequent expansion and cooling. This is a very difficult concept to grasp. It separates brane time from some hypothetical bulk time. The endless cycles would not be happening in time. Instead, each cycle would be its own self-contained history, its own space-time created anew at each collision. This would neatly solve the entropy problem. Each cycle starts with low entropy because each cycle is a fresh start for time itself. This is perhaps one of the most philosophically challenging aspects of the theory. It suggests that our deepest and most intuitive concept, the flow of time, is not a fundamental feature of reality, but a local property of the membrane we happen to inhabit. Number 3, it predicts the end of the universe could be a big crunch in disguise. The discovery of dark energy in 1998 seemed to paint a clear picture of the universe's ultimate fate. The accelerating expansion would continue forever, galaxies would recede from each other faster and faster. Eventually, they would move away so fast that their light could no longer reach us. The night sky would become dark and empty. The remaining matter in our local group of galaxies would slowly decay. The universe would end in a cold, dark, empty state known as the Big Freeze or heat death. The cyclic model of Brane Cosmology offers a completely different and more violent ending. In this model, the current phase of accelerating expansion is not permanent. It is just one part of the cycle. The dark energy that drives the expansion is caused by the potential energy of the force between our brane and its parallel partner. As the branes move through their cycle, this force will eventually change from repulsive to attractive. The dark energy will turn off. When that happens, the accelerating expansion will stop. and then it will reverse. Gravity will once again become the dominant force on cosmic scales. The universe will stop expanding and begin to contract. Over billions of years, galaxies will start to rush back towards each other. The universe will get hotter and denser. This will culminate in a big crunch, where all the matter and energy in the universe is squeezed back together into a super hot, super dense state. In the old Big Crunch scenarios, this was the end. The universe would collapse into a singularity. But in the cyclic brane model, the Big Crunch is not the end. It is simply the prelude to the next Big Bang. The crunch is the moment when our brain collides with the other brain. The immense energy of the collapse triggers the next cycle. The universe is destroyed and reborn in the same instant. So, from the perspective of someone living on the brain, the end of the universe would be a fiery big crunch. But from the perspective of the higher dimensional bulk, it's just one moment in a gentle, endless oscillation. This is a profound reinterpretation of our cosmic destiny. The lonely, cold death predicted by the standard model is replaced by a recurring, violent death and rebirth. It also means that the clues to the universe's end are not just in measuring the properties of dark energy. They might also lie in the search for extra dimensions or other signatures of Brane cosmology. If the theory is right, the cosmic acceleration we are now experiencing is a temporary phase, a deep breath before the universe begins its long, slow plunge towards the next cosmic collision. Number 2. The ultimate test is finding a deviation in the law of gravity. For all its wild ideas and mind-bending concepts, Brane cosmology is a scientific theory. And a scientific theory must be testable. It must make predictions that can be verified or falsified by experiment. Many of the predictions of Brane cosmology, like the production of mini black holes or the existence of Kaluza-Klein particles, rely on building bigger and more powerful particle accelerators. But there is another, more direct way to test the core idea of extra dimensions. That is to look for tiny deviations from Newton's law of gravity at very short distances. Newton's inverse square law of gravity has been one of the most successful laws in the history of science. It says that the force of gravity between two objects decreases with the square of the distance between them. If you double the distance, the force becomes 4 times weaker. This law works perfectly from the scale of planets and stars down to the smallest distances we have been able to measure. But Brane cosmology, particularly the ADD model with large extra dimensions, predicts that this law must break down at some point. The reason is simple. The inverse square law is a direct consequence of gravity spreading out in 3 spatial dimensions. If, at some small distance, gravity is able to spread out into more than 3 dimensions, the law must change. For example, if there is 1 extra dimension for a total of 4, the force of gravity should follow an inverse cube law. If there are 2 extra dimensions, it should be an inverse 4th power law, and so on. Gravity would get much stronger, much faster as you bring 2 objects very close together. The ADD model predicts that the scale at which this happens could be as large as a millimeter. This has inspired a series of incredibly delicate experiments. These experiments typically use a device called a torsion pendulum, where 2 masses are brought very close together at distances of micrometers to measure the gravitational force between them with extreme precision. They are looking for any sign that the force is stronger than the inverse square law predicts. So far, these experiments have found no deviation. They have confirmed that Newton's law holds down to a distance of about 30 micrometers. This has ruled out the simplest versions of the ADD model with the largest possible extra dimensions. But it has not ruled out the theory entirely. The extra dimensions could be smaller than 30 micrometers, or the geometry could be more complicated, like the warped dimensions of the RS model, which would not show up in these experiments. Still, this line of research is crucial. It is a direct tabletop test of the dimensionality of space. A positive result, the discovery that gravity gets stronger at short distances, would be one of the most profound discoveries in the history of science. It'd be concrete, experimental proof that we are living in a higher dimensional universe and that the wild ideas of Brane Cosmology are not just speculation, but a true description of reality. Number one, it fundamentally changes our place in the cosmos. For thousands of years, we have looked up at the sky and assumed that what we see is all there is. Our story of the cosmos has been one of an expanding stage. First, the Earth was the center, then the sun. Then we realized our sun was just one star among billions in the Milky Way galaxy. Then we realized our galaxy was just one among trillions in an expanding universe. At each step, our perspective got bigger, but the basic idea remained the same. The universe is the sum total of everything. Brane Cosmology represents the next, and perhaps final, step in this decentering of humanity. It suggests that our entire universe, all 93 billion light years of it, all the trillions of galaxies, is not the whole thing. You know, it is an infinitesimal slice of a much larger, higher dimensional reality. You know, it demotes our universe from the universe to a universe. This is a change as profound as the one initiated by Copernicus. It forces us to confront the possibility that the vast majority of reality is, and always will be, completely inaccessible to us. We are confined to our brain. We cannot see the bulk. We cannot travel into the extra dimensions. We cannot visit the potential parallel universes next door. We are trapped, not by distance, but by dimensionality. The very laws of physics that create our existence also serve as our prison walls. All of our science, all of our exploration is limited to studying the physics of this one membrane. And we are like marine biologists who can only study one tide pool, unable to ever know the true extent of the ocean. And this could be seen as a bleak and limiting picture, but it is also a source of incredible wonder. It means that the most fundamental questions about reality, why did the Big Bang happen? What is dark matter? What is dark energy? Why are the laws of physics the way they are? To truly understand our world, we might need to understand its relationship to the bulk and the other branes within it. This is what makes Brane Cosmology one of the wildest ideas in physics. It doesn't just add a new particle or a new force. It changes the very definition of space, time, and reality. It suggests that everything we have ever known or ever will know is just a flicker of activity on a thin membrane, adrift in an incomprehensibly vast, higher dimensional space. And the only hints we have of this larger world are in the subtle clues left behind in the cosmos, the perplexing weakness of gravity, the mysterious acceleration of space, and the enduring question of our own origin.